Welcome. I'm glad you have joined me today to learn more about supporting student sense-making in science. I'm Diane Johnson, and this video is brought to you by PIMSR, the Partnership Institute for Mathematics and Science Education Reform. This is the first video in a 5-part series on sense-making in science. These videos can be used individually or with a grade level group or PLC. The materials you will need during this session can be accessed by clicking on the link in the description box below. Please open or download a copy of the What is Sensemaking Organizer, the White Paper from McCrell, Student Learning That Works, and the Plan of Action Organizer. Depending upon your preference, you may want a pen or a pencil to jot down your ideas on the organizers and to annotate the white paper as you read. In video 1, we will explore the idea of using a sense-making frame in science. By the end of the video, you will have constructed a description of sense-making in science and will be able to identify the key components of sense-making. If you're working in a PLC, you'll have an opportunity to develop a consensus description of sense-making. Consider how to draw on the expertise within your PLC for each component and determine some possible next steps for continuing to deepen your understanding and use of them. Let's examine this definition of sense-making from the dictionary. To me, it appears pretty circuitous and like it would apply to almost any experience or discipline. So let's think about this idea of sense-making in science. What comes to mind? Capture your initial ideas on the What is Sensemaking Organizer. In a classroom where instruction is organized using a sense-making frame, what would students be doing? What would the teacher be doing? What is sense-making in science? As you jot your ideas down, you may want to capture your thinking about what supports might be needed for students to engage in sense-making and for teachers to engage students in sense-making effectively. In this video, we will focus on deepening our understanding of sense-making, and in videos 2 through 5, we will focus on the supports needed. Pause the video and capture your ideas on the organizer. If you're working in a PLC, share your thinking with your colleagues. What were some of the similarities in everyone's descriptions? What were some of the differences? What are some questions that you have or that arose from the conversation? Again, pause and share. Sometimes it helps to bring an idea to life by seeing it in action. We will watch a short video, it's a little less than 6 minutes, of some elementary students in Washington State. These students are engaged in sense-making, and the teacher is supporting the students in sense-making. I say that just so you know that that's the reason I'm showing it. As you watch the video, add ideas to your organizer that further characterize using a sense-making approach in the science classroom. Add specific things that the students are doing and specific things that the teacher is doing or appears to have done. After the classroom video, pause and add to your descriptions, definitions of sense-making on your organizer.
Let's review the rules when we are having a science discussion. What are some of our agreements?
We know when to talk when nobody else is talking.
What about if you notice that somebody isn't sharing?
You can work together to try to share and solve your problem.
You bring them into the party.
You bring them into the science party, into the science discussion, exactly. The one thing that we worked on last week was where we had our Legos. What do those Legos represent?
Legos represent building on each other's idea.
Okay, so remember today as we start getting into our science discussion here that we're building on each other's ideas. So what we learned about and what we've talked about the past couple of days is what might increase the rate of erosion. This was a model for a river, and when we increased the angle a little bit, can somebody explain what the water flow was like?
The water kept going faster, like when it was 10 degrees.
It took 4 seconds, but it was 55 degrees. It took 1 second.
The erosion forced it to go faster.
So that's a great place to start our claim. We think that increasing the angle of the stream table will increase the rate of erosion.
It left us with a lot of canyons plus the delta, which made it pretty interesting.
Let's see if we can see Christian's group up on the screen to see the rate of erosion with theirs. So we're looking for that increased rate of erosion. I mean, look at that. What is that even in 20 seconds? In 12 seconds it went through. Okay. How do we think this connects to our phenomenon and the mysterious landscape? My name's Jennifer Witten, and I teach 4th grade at Beaver Acres Elementary. And what you saw today was the end of about a 2 or 3 week unit where our class has been working on a phenomenon. Started the unit showing them some pictures of a landscape in eastern Washington. It didn't explain how the land was formed. So what the students did after watching that was they created their own model of what their thinking was about how this landscape was formed.
This project is about discovering what created those weird holes. When we did our experiment, maybe do you remember when the water started falling? It made a hole on the sand. Maybe it made a huge hole on the sand and made those black holes.
Oh my god! It's creating the delta.
Oh, there's another one.
I think there was a little hole and the water started coming in, and then it created more cracks because the water was coming in, and it created more holes and more, and it created bigger, which created a canyon, and that relates to our string table.
Those holes are from those rocks, and then the water moved those rocks to a different area, and then made multiple.
What do you think, Kashmir?
I go with Nicholas's idea.
Experiment 1, which most represents the landform.
I think it would be experiment number 3, because number 3 added more water, and it was like more efficient. Maybe there was more water than less water. We pulled up the old video to see which one was more efficient, and I think it was number 3 because there was like a little delta and the whole thing almost collapsed.
This process started with watching a video of the landscape in eastern Oregon. And Mrs. Witten asked us what caused it, and what we thought was the waterfall. And then we did a few experiments to figure out what caused the landscape, and now we are making a model of what we think happened.
I'm just gonna give groups about 1 more minute, and then we're gonna have a board meeting. We're gonna meet and present our ideas, okay?
We used to think that a drought dried the ocean up and a volcano caused the soot and ash. Now we think that a flood caused the canyon and carried the boulders to random places, and the water pressure caused the holes. And the stream table experiment supports our idea because when the water hit the land, it made a canyon and caused erosion.
Any questions for this group?
Is there still a volcano in this or no?
No.
How did the bits of rocks make the ash?
The water chipped away bits of rock.
Today what you saw was this board meeting where they revised their thinking. They had to include all the ideas from the activities that we did, and tomorrow we will watch the entire video and they will be able to see if what their theory validates what really did scar this landscape. This is part of some practices that have come with the next generation science standards. What I've been most excited about with these standards is the role that language plays in science, and I find that these standards really align well with language development. As you saw today, the students have a lot of time to share their thinking, their reasoning, they're using evidence to support their thinking, and then they're explaining their ideas and changing their thinking. All of those are science practices, but they're improving their language through learning new content. And as you can see, it's really engaging. Students are 100% engaged, and they're really doing some incredible work in here, I think.
Take a minute to just think about the things that you saw in the video with the elementary students. If you're working in a PLC, you want to share your additions. A strategy you might want to use for sharing would would be to allow each person to share one idea. Everyone listen, see if they have a similar idea and put a check on their list. If you don't have that idea and you agree with it, then add it to your list. Move on to person 2, who then shares an idea that's different from what the first person shared. As a PLC, develop a consensus of what seems to be the key components in a sense-making classroom. Generate a group list for supports needed by the students and for the teacher. Pause this video and build your consensus description of sense-making in science. For many of us, we learn science as a collection of facts, definitions, and equations to be memorized. The tests we took were basically tests of our memorized definitions and equations, and were focused on right answers. Generally, the teacher's role was to tell us what we needed to know. We took notes. Maybe we did something hands-on to verify this knowledge. This framework for learning science often created misconceptions about what science is and how it works. It made it seem that science wasn't accessible to everyone. Using a sense-making frame, we're focused on understanding science concepts, not just facts, definitions, and equations. We're learning about the mechanisms that help us understand how the natural world works and how we've come to figure that out. The teacher's role shifts from telling to providing phenomena to figure out and supporting students in using the same practices that scientists and engineers use to figure things out. Instead of tests being about facts and right answers, we provide students with a phenomenon, a scenario to figure out using evidence and the science ideas that they've been learning in class. Take a minute to reflect on where you feel you are on this continuum of science instruction. What evidence did you use to place yourself at this spot on the continuum? If you're working with a PLC, pause the video and take a few minutes to discuss the continuum. And consider why it might be important for your students, for the teachers of science in your school and district to develop and use a similar framework for instruction. What areas of expertise among you can help you grow as a team? What are areas of need for professional development? After we discuss the components of sense-making, you'll have an opportunity to revisit these questions and draft a plan of action. Take a minute, pause the video, and discuss this continuum. Sense-making is actively trying to figure out the way the world works for science questions and exploring how to create or alter things to achieve design goals for engineering. This quote comes from a book, Helping Students Make Sense of the World, that I have found very helpful in developing an understanding of sense-making in general and the science and engineering practices in particular. There's a link to this book on your selected resources table, and we'll have more information about this in video 4 as we examine how to leverage the science and engineering practices to support sense-making. A framework for K-12 science education, a free resource from the National Academy Press, is another essential resource for developing an understanding of sense-making. There's a link for that on your resources table as well. As teachers, to quote Brian Goodwin, we are in the profession of turning experience into memory. And effective teachers use what research suggests about learning to design and deliver instruction for our students. I've included a white paper from McCrell, authored by Brian Goodwin, that provides a nice distillation of what we know about brain science to inform a model of learning. Many of you may be familiar with McCrell. It's one of the educational labs, and at one point, Robert Marzano was the director of McCrell. Now it's Brian Goodwin. And so they have continued to do a lot of research into learning and best practices. The graphic on the slide is a model of learning using brain science that McCrail has put together and detailed in a white paper. The white paper is a summary from a book called Learning That Sticks, a brain-based model for K-12 instructional design and delivery. Your resource table has a link to the white paper and to the book for anybody interested in learning more. So take a minute and just look at the graphic to see what are the main components of this brain-based model for learning. And think about, is there a connection for this brain-based model of learning and a sense-making approach, a sense-making frame for helping students learn science? Let's consider this a little bit more. Access the white paper, Student Learning That Works, and think about this idea of sense-making as we've been discussing it and what we know about learning. Are they compatible? Use the information organized into a table on pages 6 through 9 of the white paper. Highlight ideas that align with those you've noted on what your sense-making is, organizer. What things did you see in the Beaver Acres Elementary School video that are compatible with this learning model? Add any additional ideas you gleaned from the table on your sense-making organizer. Pause the video to consider if using a sense-making frame is compatible with brain science. If you're working in a PLC, share your thinking using evidence from the learning model on pages 6 through 9 and from the classroom video. After you've had a few minutes to read those pages and synthesize the information, pause this video and discuss the compatibility between sense-making and brain research. Now let's take a moment just to pause and reflect on where you feel some of your strengths are and some of your needs are with respect to just sense-making in general. Note some resources that you have. Maybe some of those that are on that table that you have, or some that you might need. Identify some next steps. What are some things that you think would help you up your game with respect to using a sense-making frame of instruction with your students? And then hold yourself to a time frame for implementing and evaluating yourself on these. So take a moment to pause and reflect. If you're working in a PLC, you may want to compare each other's plan of action and think about what are some needs for every member of your PLC. What are some strengths of each of your members that you can leverage? Restart the video after you've had a chance to reflect and plan. As a member of the NSTA, National Science Teaching Association, sense-making cadre, I have had the opportunity to really dig into this idea of helping students make sense of the world and to explore a range of resources to deepen my understanding. NSTA leadership and cadre members have developed and collected a wealth of materials to support teachers moving to a sense-making frame of instruction. The icon on the slide depicts the components of sense-making that need purposeful consideration and development with the goal of supporting science learning for all, equity, in the classroom. These components come from a framework for K-12 science education. which used what we've learned from brain science, neuroscience, educational research, and science education research to suggest instructional shifts and to develop the next generation science standards from which our Kentucky academic standards for science are derived. We're going to briefly discuss each component. As we do this, jot down things you're currently doing with respect to the component and things to consider doing to strengthen the sense-making experience for your students on your plan of action organizer. Each component is essential for supporting students' sense-making, and their use isn't linear. I'm going to start with science ideas because that's generally where we start our planning. What is it we want students to know and be able to do by the end of an instructional sequence? Fortunately, we have the Kentucky Academic Standards for Science to narrow the scope of science ideas we want our students to understand by the time they exit our K-12 system. As we noted earlier, a sense-making frame is focused on concept development. Those concepts are detailed as disciplinary core ideas in the framework, in the science standards, and in the cross-cutting concepts. I have found that an NSTA publication, Disciplinary Core Ideas, you can see a picture of this on the screen, has really helped me to dig in and consider what are those big ideas? What do we mean by conceptual development of those big ideas? And the book even gives some possible experiences to consider for developing understanding. The performance expectations on our standards tell us what students should be able to demonstrate at the end of a grade or a grade band. They were written for large-scale assessment developers. The disciplinary core ideas, the DCIs, tell us what concepts we want students to come to understand. So as you plan experience for students, you want to focus on the DCIs, not the PEs. You want to make sense of the DCIs. Don't look at the page and think topic like erosion or water cycle, but think big transferable ideas. Examining the DCIs through the lens of a cross-cutting concept or two is also helpful. Think about why students need to understand this, and that will help you move from topic thinking to concept thinking. For example, if we want students to be able to explain why the Earth's surface looks like it does and to predict how it might look in the future, students would need to consider energy and matter flows, cycling and conservation among the Earth's systems. They would need to consider causal mechanisms for landforms they observe and why we need to understand those mechanisms since we depend upon Earth materials. This leads us to how we design experiences for them to come to this understanding. Next, to develop conceptual understanding, you need something to make sense of, to figure out a phenomenon. As we saw in the classroom video, students weren't figuring out what is erosion. They were trying to figure out how a specific landscape in Eastern Washington was formed by making observations, generating questions they had, planning and conducting investigations to answer their questions, sharing their data and the implications of their data, and communicating with others about their observations, questions, and data to construct an explanation for that landform. As their ideas emerged, the teacher helped them to clarify their thinking through questioning, summarizing findings, and providing appropriate scientific terminology for their observations so they could communicate more accurately. An observable event in the universe, a phenomenon, provides the reason we need to figure this out, a reason we need to understand these concepts or to read this article, book, or paragraph, while providing something tangible that all learners can connect with and bring their background knowledge to help question and explain. In video 3, we're going to do a deeper dive into phenomena and how to use them to develop student understanding. As you can see on the screen, there's a few links to resources that you might find useful. for just helping you think of phenomenon to consider. These are also contained on your resource table. As you noted in the model of learning, we have to get the brain's attention. That's the phenomenon. We have to commit to learning, like, why should I care? And help students make connections with what they already know and what they need to know to figure something out. Learning is a social endeavor. To help the ideas become a permanent part of our long-term memory, students need opportunities to make connections, to discuss their ideas with others, to try out their thinking, to get feedback on it, build on ideas of others, question their own thinking and the thinking of others, and to change their thinking in light of new evidence or the ideas from others. This requires a classroom environment that is a community of we. We think this, we figured this out, we want to know. It also requires learning how to think like a scientist or an engineer and to communicate effectively with others. Teachers want to build a community that values the thinking of everyone, that allows for learning from mistakes and changing our thinking without penalties, that helps us have productive academic discourse about a phenomenon we're trying to figure out, and helps us keep track of what we know so far. Video 4 will focus on strategies and supports for leveraging student ideas. I've shown a few on this slide, just a driving question board, having a driving question to focus a unit around that phenomenon, using discussion guides. How do we talk to each other? Think about the video that we saw where they were focusing on building on each other's ideas. How do we communicate in scientific ways? So we might provide prompts, as the teacher in the video did. Here's some ways that we can discuss sharing ideas of others, or use of evidence, or limitations of an investigation. So these resources are also on your resource table. The fourth component necessary for sense-making in science is how students will make sense of the phenomenon by developing and using the elements of the science and engineering practices. As we noted with the disciplinary core ideas, we want to provide experiences that allow students to use a specific element or a part of a specific element appropriate for their grade band. For example, students in the video were going to construct an explanation for the landform in Eastern Washington, but more specifically, they were going to use evidence, such as measurements, observations, patterns, to construct or support an explanation. Just like the disciplinary core ideas, we have to design experiences for students to use specific elements of the practices and help students develop their understanding of the practice. Additionally, we want to support students in leveraging specific elements of the cross-cutting concepts as thinking lens in tandem with the practices. In this example, students would need to come to understand what counts as evidence, what isn't evidence, how to identify patterns and observations in data, and what might be causes for those patterns. Appendix F contains the matrix of practices organized in grade bands, and Appendix G contains the matrix of cross-cutting concepts organized into grade bands. The framework in the book, Helping Students Make Sense of the World, are additional resources for helping students engage in the practices. Video 5 will dig into these practices and explore ways to help students develop and use them. We touched on the idea of building an equitable classroom community of curious and critical thinkers when we discussed the students' ideas component. But establishing an equitable classroom where everyone's voice is heard and valued, and providing multiple ways and opportunities for students to demonstrate understanding requires the teacher to very purposefully and explicitly build that community. We'll also discuss community building and specific strategies and supports for doing this in video 4, along with leveraging student ideas. Your resource table contains a link to the Open SciEd resources, where you'll find the types of discussions, classroom norms and how to establish them, a range of supports for building this community that are shown on this slide. I just did a whirlwind overview of each component, but I hope I got you thinking about each one and considering where you are in leveraging each to design and deliver instruction. Let's take another opportunity to reflect and to plan next steps. Access your sense-making plan of action organizer. Again, if you're working in a PLC, allow each member a few minutes to reflect individually and to capture their ideas on the organizer. Then take a minute to compare strengths, needs, resources, and next steps. Develop a plan of action as a PLC based on your comparison to sense-making and each component. Restart the video after you've had a chance to reflect and plan. This video aimed to help you construct a description of sense-making in science and to deepen your understanding of using a sense-making frame for designing and implementing learning experiences. We accessed your prior knowledge and applied and extended that for developing your description by noting sense-making in a video of an elementary classroom. From there, we took a 50,000-foot view of the components of sense-making and noted some resources for each component. We paused along the way to reflect and plan some next steps. If you've been working in a PLC, you've had the opportunity to begin to develop a consensus model of sense-making with your colleagues, and we're able to tap into all the expertise each of you brings while determining your collective needs and strengths. Some quotes from the book, Learning That Sticks, I think are really relevant to maybe sum up this idea of using a sense-making frame in science. First, we encode only what we think about. And so the students have to be the ones doing the active processing, not just passively receiving information. To learn anything, students must concentrate on the meaning, the why, the how, the connections of what they are learning. And that's where having driving questions, a phenomenon, a reason for understanding this is so important to help the students pay attention to it and want to know more. At the heart of sense-making, all learning really, is connecting what we're learning with what we already know. So by making those connections with, here's a phenomenon, here's these activities that we're exploring to give us some data, where are other places that you may have seen this or noticed this? We can help students develop conceptual understanding and transfer that learning. In this session, we began to build an understanding of sense-making in science. In subsequent sessions, we will dig into each component of sense-making. In session 2, we're really going to dig into clarifying science ideas. What are those big conceptual ideas, the disciplinary core ideas, and what are some resources we can use to help us think about that? I look forward to sharing with you again as we continue our deep dive into supporting student sense-making in science in sessions 2 through 5.